All right, so one of the fundamental examples for uniform circular motion is the loop-the-loop, right? And so if you're not familiar with this, that's a giant vertical loop, right? And either a motorcycle is the historical example, right? Or a ball or really anything, right? In this case, it's a ball. It starts at some height and it travels down this ramp and it continuously then goes up this loop. And we're wanting to find the minimum speed required to maintain contact to complete the loop, right? So actually, if it completes the loop, it's going to come down and travel out safely, right? In other words, it will not come up and then either fall back down, or it will not go up and just kind of fall off and fall back down there, right? It's going fast enough to maintain contact the entire way, okay? So what's the critical point, right? The critical point, right? The minimum speed, in other words, is really at the bottom. We have to have the minimum speed at the bottom because as it loses speed going up, it still has to be going fast enough to maintain contact at the very top, right? So if it maintains contact at the very top, then it will continue on in contact the entire way. So the main thing is that what's the minimum speed at the bottom, right? If it goes faster than that, then it's guaranteed to stay in contact. So let's see. This is a ball of mass m, right? And this is a radius of 10 meters. It's a giant vertical loop-to-loop. Okay, just go with it. So we want to find the minimum speed at the bottom. Well, we can do a free body diagram analysis here, right? Here, it's not necessarily going in uniform circular motion yet. It is, but it isn't, right? A better place to do it, whoops, come back. A better place to do it is either on the side here or up top, right? Or rather, anywhere up here. So I'm going to choose to do it at the top, okay? At the top. So let's see what's going on here. What are the forces on this ball if it's in contact with the surface at the very instant it's at the very top? Well, there's always gravity. So in red, I'll draw mg, always gravity. And there has to be another force, right? It's not MA, right? It's not the total force, it's not the net force. Another Newton's third law force has to be the normal force, right? It's in contact with this surface. So that means the normal force is the surface pushing back on the ball. Well, that's also pushing it downwards, right there. This is a special case of when both the normal and gravitational forces are in the same direction, right? Usually they're in opposite, right? But it so happens that for uniform circular motion, in this case, they're in the same direction. And those are all the forces on here, right? I will say, right, I should note that this track does have friction, right? But you can also do this problem if it's completely frictionless, right? You can idealize this problem to when it's completely frictionless, and there's still only these two forces in the vertical direction, right? So if we put our axes on here, the forces in the x direction, I'm just going to say they're 0 for right now. It turns out we won't need the forces in the x direction. In the y direction, if positive is down, I'm free to choose. We have normal plus mg, right? And so we add them all up and they equal ma. not linear acceleration. Remember, this is centripetal acceleration because now the ball is undergoing uniform circular motion. And so we want to find the speed, right? We want to find the minimum speed. Well, speed is embedded in centripetal acceleration. So let's write that as mv squared over r, okay? And let's see here. We have Fn plus mg equals mv squared over r. Okay. Do we know mass? Turns out we won't need it. G is a constant, r is given. We're finding speed. The normal force right here, actually, let's just circle that. The normal force, do we know that? No, we don't. But let's put on our physics thinking caps a second. If we want to find the minimum speed required for this ball to maintain contact the entire way up the curve, what if just at the instant it reaches the very apex, it were to lose contact? Right? Just before that instant, it loses contact. Well, that means that when it's at the very top, it's not in contact. So we can assume that the normal force is 0 in this special case. Right? If we assume the normal force goes to 0, then we have mg equals mv squared over r, and we can solve for v. Masses go away, and it's just square root of rg, right? You plug in 10, plug in 9.8, take the square root, and you get about 9.9 meters per second. Now, this is the minimum speed, so it's not necessarily 9.9. The minimum speed is 9.9. So we need actually, if it is to remain in contact the entire way, we need it to be going faster than 9.9. So the speed to be in contact has to be greater than 9.9 meters per second. Okay, that's another way to say this. Okay, so the free body diagram analysis here was relatively simple. The thing to note is that the normal force and mg happen to be in the same direction, and we set them all equal to the total force, ma, right? Just like before. However, in this case, because it's undergoing uniform circular motion, that net force was mac, not just ma. And we can rewrite that as mv squared over r, and thus solve for the speed as it's moving in the circle. Okay. Sometimes you won't have a vertical circle like this. Sometimes you may have a horizontal circle, right? You still do the free body diagram analysis the same way, but if it's moving in a circle, make sure to do mv squared over r, okay, in that direction. All right, thanks for watching.